In this lecture, I'm going to talk about tunneling field effect transistors. This is a new type of switch that changes how the transistor operates from thermally exciting electrons over a barrier to tunneling through a barrier. So here's an outline of this lecture. So in the first part, I'm going to give an overview and kind of just talk about the basic WKB derivation of tunneling. Then I'm going to talk about the two ways to get steepness in a tunneling switch. We can either control the thickness of the tunneling barrier, or we can use energy filtering, where we cut off the electrons that can tunnel. Next, I'm going to talk about p-n junction dimensionality. And the idea here is that the exact dimensionality, 1D, 2D, or 3D, can very drastically change the density of states in a switch, and will therefore change the nature of its turn-on. And then lastly, I'm going to talk about how do you take a tunneling junction and turn that into a full TFET, and what will be the subthreshold swing and gate efficiency that you would get. And then finally, I'll talk about some additional issues and give us an overview. And so first, let me kind of just review what was wrong with current transistors. So in a current transistor, we have a thermal distribution of electrons in the source. So what this means is that to turn off the transistor, we typically move this barrier up by, say, a factor of kT. We block the current, but we can only block the current by a factor of E. And that's because the electrons follow this thermal distribution. So now if we want a large on-off ratio, we need a large voltage, typically a few hundred millivolts. And so we want to change how the transistor operates. And so the way to do that is we're going to change it from going over the barrier to tunneling through the barrier. When we do that, there's two ways we can get a sharp turn on. The first is we can control the thickness of the tunneling barrier. So as you can see here, we have a very thick tunneling barrier. It'll be very hard to tunnel, and it'll be hard to get any current, so your device is off. But now when we apply a voltage to the gate, we can pull this barrier down, make the barrier thinner, and then get a much higher tunneling current. And so, in principle, this will allow us to turn our device on and off, but what we'll see later on is that this really ends up only being steep at low current densities. And so what we would like to use is an alternative mechanism called energy filtering or density of states switching. And that's illustrated here. So in this conduction band and valence band don't overlap, there's no states to tunnel to, and so no current can flow. Then ideally, we just apply a little bit of voltage, pull this down, and we get an overlap, and we get a very sharp turn-on. The problem, as we'll see later on, is that there's actually states that exist below the band edges, and so then we end up tunneling to those states, and that's the steepness of the turn-on. So now, kind of to give an introduction to this sort of whole concept of tunneling, I want to kind of just analyze the very conventional WKB approach to tunneling in a nanowire. And so I just want to kind of ask, what is the current that I have going through this band diagram? And so we can notice a few things. One is that you see that our conduction band and valence band only overlap in this regime. And so what that means is that current can only flow here. And so then naturally what we want to ask is how much current is flowing at each energy, and then just integrate over that to get our total current flow. And so to start, let's just assume the valence band is full, conduction band is empty. So we can have tunneling occurring at all of the energies where it overlaps. And so then what our current will be given by is just sort of the charge times the velocity times the density of states. And then we have this barrier in the way, and so we have to multiply it by a tunneling probability. So if we do that, we can take our velocity to be the momentum divided by the mass, so h bar k over m. And then we do the 1D density of states, that's given by this. And then for now, we'll just call our tunneling probability some factor t. So if we multiply this, almost everything cancels. And what we end up with is our current is 2qh times delta E. So that's basically sort of how wide is this energy window times the tunneling probability. And this basically gives us our quantum of conductance. And so there's a couple of interesting things to note. One is that if the tunneling probability is the same at all these energies, the current, or the conductance is the same at all the energies. And so we just have to multiply this window, the width of this window, times the quantum of conductance times the tunneling probability. Another interesting thing to note is that this current is a velocity times the density of states, but that changes quite a bit as we go through the device. So for instance, over here, we were very close to the valence band. The holes don't have much energy, so they have a low velocity, but they have a high density of states, just because the 1D density of states is very high near the band edge. Then as we tunnel across, we end up in a region where the electrons have a very high velocity because they have a lot of energy, but they don't have a very high density of states. But the product still cancels and is the same, and we always end up with this quantum of conductance. And so then that's kind of just how you would see what's the tunneling current through a nanowire in an ideal situation. And so here I just kind of want to contrast that to sort of a conventional, say, conventional barrier, 1D tunneling. So let's say if you look at this band diagram here, what we have is just a simple tunneling barrier and then say two metallic wires on each side. And it's set by, if we have a Fermi level here and a Fermi level here. And so typically you would say, in this case, we would just have current flowing in the overlap between the two Fermi levels, so in this region. But then it would still be a quantum of conductance. It's 2e squared over h times the source drain bias times the tunneling probability. And so this is very similar to what we saw in the band-to-band nanowire case. The only difference is that instead of the relevant energy being set by this Fermi level splitting, it's set by the difference between the two band edges. And so that's why we get this overlap voltage. And the reason for that is we're assuming that our conduction band and valence band are full. And so that means that we have a reasonable Fermi level splitting above that. And so then this is tunneling current through a simple nanowire. And now so far, I haven't addressed what is actually that tunneling probability. And so to understand that, we can consider a simple rectangular barrier. So here, let's say we have a free electron. So it's a free electron, its wave function is just going to be a simple exponential, e to the I kx, where your k is just given by your energy, square root of 2me over h bar squared. And then same thing when you're on the other side of the barrier. But now the question is, what happens to the wave function when you're in the barrier? It ends up being the same form. The only difference is that this k, your energy is no longer this energy, but rather you have a negative energy because your potential is up here, but your energy is down here. And so you have this negative energy, E naught minus V naught. What it means is that our k becomes imaginary, and so then in e to the I times kx is you basically get a decaying wave function. And so you can see that here. We have our free wave oscillating, and then we have this exponential decay as we go into the barrier. And then it's oscillating again once it's out. And so then the tunneling probability is essentially given by this decay factor. But now we have to square it, because we want to know what's the probability, and probability goes as the wave function squared. So that just becomes, we had e to the minus kx was our wave function. We just square that, and so we get a 2 here. And then that k, again for the rectangular barrier, was very simply the square root of 2m over h bar squared times that negative energy in the barrier. So now we can already see from here kind of what are the factors that allow us to have a high tunneling probability or a low tunneling probability. For instance, the thicker the barrier is, the lower the tunneling probability. And also if we have a high barrier height or a heavy effective mass. So like things we want for high tunneling probability would be a thin barrier, small barrier height, and light effective mass. Now, we can extend this further if we want to say have a barrier with a shape that's different from it's a rectangular barrier. And this is sort of that WKB approximation. Basically what we just say is that we just divide the barrier up into a bunch of small pieces. So let's say we have this triangular potential. What we can say is that in this piece we will have some k and some delta x. And then similarly we'll have another little segment of barrier with a slightly different k and then the little unit. And so then we just sort of multiply the tunneling through each of these small segments. And when you do that, you basically just get an integral. The tunneling probability is e to the minus 2 integral from 0 to L of k dx. And so then you can go through and evaluate this for, say, a triangular barrier where we have our field is constant, and so that means our potential is just dropping linearly. And if we do that, what we find is that our tunneling probability is minus 4 root 2 square root of the effective mass times the barrier height to the 3 halves divided by 3 h bar q times the electric field. And so then that kind of gives you an idea of what's tunneling probability. And again, you can see what are the key factors for a high tunneling probability. You want a high field, you want your barrier to fall off quickly. You want a small barrier height, small effective mass. Now we can extend this a bit further. So far we've talked about tunneling through a single triangular barrier in one band. So you have electron coming in and going out. But now let's say we're trying to do band-to-band tunneling. How would we model that? So the simplest way to look at it is that you just have two triangular barriers. Initially your electron is just tunneling through the closest band. And so it's this triangle. But then once we reach mid-gap, it's closer to the energy is closer to this band. And so now we're tunneling through this barrier. And so you can do that and just multiply the probability of two triangular barriers. Or if you want to do it a little bit more accurately, you should essentially smoothly transition from one band to the other. And you just kind of round off that transition. And that's sort of covered in here. But the key is you get almost the exact same expression. All that changes is this prefactor. Whereas it used to be a 4 root 2 over 3, now it's a pi over 2 root 2. It's just something to be aware of. You get all the same key material parameter dependencies, but it's your two-band tunneling changes your prefactor a little bit. And then here is sort of the effective mass for the two bands. It's essentially an averaged mass between the two, or type of average.